Let's take a look at a force. A force is the cause of linear motion. Then there are three main properties of force. The first one is magnitude. So depending on the magnitude of force, the effects of force on the system will be different. And the second property is the direction. So depending on the direction of a force, the effects of force on system will be various. And then the last property of force is point of application, which means where force is acting. So depending on where force is acting on the system, the effects of force on system will be different. Let's take a look at this figure. You can see there are three arrows here. These are all ground-reaction forces coming from the force plate to this body. The length of this arrow means the magnitude of force, and tip of this arrow means the direction of force. And if you take a look at bottom here, you can see the center of pressure, which can tell us where this force is coming from. So this one is point of application. Let me briefly explain Newton's laws of motion. There are three laws of motion here. The first law is law of inertia. This law of inertia can be defined as a body remains at current state of motion unless acted upon by an external force. Here, current state of motion means current velocity. And then here's an example of law of inertia. Static inertia versus dynamic inertia. So if you understand the difference between these two, so you will be able to easily understand law of inertia. Here, static inertia means if an object is not moving, the object has a tendency to be stationary. Dynamic inertia. If an object is moving, the object has a tendency to keep moving. There's a difference between static inertia and dynamic inertia. And second law of motion is law of acceleration. So this law of acceleration can be defined as a force applied to a body causes acceleration. In other words, if a force is larger than friction, the force causes a motion. And once a motion occurs due to the force applied, the motion is supposed to have an acceleration. That's why you can see F is equal to ma, which means force causes acceleration. And then the third law of motion is law of reaction. So this law of reaction can be defined as for every force or for every action, there is an equal and opposite reaction. Here equal means the same amount of force, and opposite means opposite direction. So ground reaction force can be the example of law of reaction. Let's take a look at this figure here. You can see two arrows here. Black arrow represents force acting to the ground, and then red arrow represents ground reaction force. If you take a look at these two arrows here, lengths of these two arrows are the same, which means the same magnitude, equal direction, but they are acting in an opposite direction. So that's why this ground reaction force, the example of law of reaction. Free body diagram. This is a simple sketch of the body that includes the forces and moments of force and geometry of mechanical systems. Then this is example of free body diagram. So this one includes all the forces or the moments acting on this system. Okay, for example, here F means ground reaction force, W means the body weight, Fj means net joint force, Mj means net joint moment, Tg means a twisting moment acting at the center of pressure. And this free body diagram is very useful in visualizing mechanical problems. So in order to solve this mechanical problem, so we need to draw a free body diagram first. Then we need to derive the equations of motion of the system. After that, we need to substitute known numerical values in the equations of motion. Lastly, we have to solve the equations for the unknown terms. Types of force. In this video, we will focus primarily on the forces acting on the human body. And the first type is ground reaction force, which can be defined as a reaction supplied by the ground. And that is example of ground reaction force. ground reaction force has three components. Force acting in the medial lateral direction is Fx, and force acting in the anterior-posterior direction is Fy, and force acting the vertical direction, Fg. You can see Fg, Fx, Fy. In this free body diagram, here F means the vertical ground reaction force. And the second type is the gravitational force. This means actually body weight. You can calculate body weight by multiplying body mass times gravitational acceleration. So in this figure, W means the body weight or gravitational force. Next type is a free moment. Okay, this free moment is a twist moment about z-axis at the center of pressure. So in this figure, here Tz is a twisting moment about this z or vertical axis at the center of pressure. And next type is net joint force. This one is defined as the sum of all forces acting on articulating surfaces. So in this figure, Fj, this is a net joint force. And this one also reflects the net effects of the action of muscles and ligaments. Next type is net joint moment or net muscle moment. And this one is defined as the sum of all the moments acting on the joint. If you take a look at this figure, Mj, this one represents net joint moment. Again, this net joint moment reflects net effects of muscle activity at a joint. And ground reaction force can be used to calculate some linear kinematic quantities, such as center of mass acceleration. Here, cm is center of mass, and center of mass velocity, and center of mass position. Let me explain this free body diagram first. Here, F means vertical ground reaction force, and W means body weight. The V means center of mass velocity. R means center of mass position relative to the origin. First, we can calculate the center of mass acceleration using Newton's second law of motion. F is equal to ma. Here, F can be net force. Net force means vertical ground reaction force minus body weight. This one is equal to body mass times center of mass acceleration. So you can divide this net force by body mass. Then we will be able to calculate center of mass acceleration. After that, you will be able to calculate the center of mass velocity by taking time integral of the acceleration calculated here. But this value, this calculation does not give us the instantaneous velocity, but give us the change in velocity during the time range from Ti to Tf. We need to know the initial velocity to calculate the center of mass velocity. But this one, initial velocity, typically 0. And after that, we will also be able to calculate the center of mass position by taking the time integral of the cm velocity calculated. So this calculation will give us a change in cm position, so that we have to add the initial center of mass position to this change in the center of mass position, so that we'll be able to calculate the cm position. Ground reaction force can also be used to calculate some linear kinetic quantities, such as center of mass mechanical power and the center of mass mechanical work. And power is equal to force times velocity. So here force can be net force and velocity is the cm velocity. So by multiplying these two, we'll be able to calculate the center of mass mechanical power. Center of mass mechanical work. Work is calculated by the integral of force with respect to the displacement using a force and displacement graph. And this calculated work causes a change in the kinetic energy of a body. This is a work energy theorem. This red part here, this part shows us how mechanical work causes a change in kinetic energy of a body. So we can use this kinetic equation for that. Here Vf means final velocity and Vi means initial velocity. So A means acceleration and D means displacement. So this question can be solved for AD. And then work is defined as force times displacement. Force is equal to MA. Then we got AD here. So this AD can be inserted into right here. Finally, we can get the mechanical work is equal to 1 over 2 mvf squared minus 1 over 2 mvi squared. And this is a final kinetic energy. This is initial kinetic energy. This is a change in kinetic energy. So the work causes change in kinetic energy. Ground-reaction force also generates torque. This is the cause of angular motion. This is origin of force plate. And F is ground-reaction force vector. The R is the position vector drawn from the original force plate to this center of pressure. Again, Cp means center of pressure. And then we got angle here. This angle formed by the line of the position vector and the line of force vector. And the magnitude of the torque produced by this ground-reaction force can be calculated using this geometric definition of cross product. So R, F, sine theta. And this torque can also be expressed using algebraic definition of cross product. Again, here M means torque equal to R cross F. And then position vector R, this one has 3 components, X, Y, Z. And then this ground-reaction force also has 3 components, Fx, Fy, Fg. So you can do the cross products using these two. Then the answer will be like this. And this one is a vector form of this moment or this torque. And then this vector form of torque can be described in matrix form. This is a actual matrix form of the moment produced by this ground-reaction force. In this matrix form, the position vector R is described using symmetric form of vector R. Then we have these force components. Then if you multiply these two matrices, the answer will be like this. But actually, these are equal to this value. Ground-reaction force can also be used to calculate net joint force and net joint moment. And here we have Euler's laws of motion. Here F means force, P means linear momentum, the M means moment or torque, L means angular momentum. And here I means moment of inertia, omega means angular velocity, alpha means angular acceleration. And then P prime means the rate of change of linear momentum. The L prime means the rate of change of angular momentum. According to this Euler's laws of motion, the sum of the forces acting on the body is equal to the rate of change of linear momentum. And then this rate of change of linear momentum is equal to ma, because time derivative of linear momentum is ma. And also, the sum of the moments acting on the body is equal to the rate of change of angular momentum. And then this rate of change of angular momentum is equal to, so moment of inertia times angular acceleration, because the time derivative of angular momentum is I times angular acceleration. And then based on this free body diagram here, the sum of the forces acting on the body are W, so body weight, and then vertical ground-reaction force and net joint force. And this one is equal to the P prime according to Euler's laws of motion. And based on again this free body diagram, the sum of all the moments acting on this system are R cross F. This is a moment produced by the ground-reaction force. And then Mj, so net joint moment, then Tg, a twist moment. This one is equal to L prime, the rate of change of angular momentum. And then you can solve this one for Fj, and you can solve this for Mj. All these black components are known value. And then again here, this one can be solved for Mj because all black components are known value. This process is called inverse dynamics. Ground reaction force can also be used to explain the impulse and momentum theorem. And this theorem tells us that the impulse causes a change in linear momentum. Then impulse can be defined as the accumulated effects of force exertion over a period of time. And when a researcher wants to know the influence of a force that changes over each duration of the application, this impulse momentum theorem becomes very useful. And then this theorem can be derived from F is equal to ma, which is Newton's second law of motion, and acceleration is the time derivative of velocity, so it can be F dt is equal to m dv. Finally, taking the time integral of both sides will generate the impulse momentum theorem. And then we have a force and time graph here, and then Ti means initial time, and Tf means the final time. So this area means impulse, also the change in linear momentum. For the integral calculation in impulse momentum theorem, this trapezoidal method is often used. Let's take a look at this figure to better understand the trapezoidal method. And then we have a time and force graph here. And then I highlight this one to show you how to calculate this area by using trapezoidal method. Then we have Fi, mean force at this point, and Fi plus 1, force at this point. And then delta t, time elapsed, but it can be a unit time. And then we have to add these two forces, and then divide this by 2, and multiply this whole by unit time. Then we can calculate area of this part. And then you can keep repeating this one until we get all the impulse during this time range. And measurement of a force. So you can measure a force using force transducers, such as a Forceplate, a pressure distribution sensor, isokinetic device. And then this is a typical setup of Forceplate. So we have Forceplate here. This one can be connected to the amplifier and AD converter through a cable. And then finally, this can be connected to the host computer. Let me tell you how force transducers can measure a force. There's a sensor in force transducers. When a force is applied to force transducers, the force results in the deformation of the sensor that serves as a resistor. Then the deformation causes its electrical resistance change of the sensor. This electrical change alters the voltage change. And there is a direct relationship between voltage and force in a circuit. So the voltage is proportional to the applied force. So this relationship allows us to calculate the force applied by measuring the voltage change. And the quality of the force transducer can also be assessed using this relationship between voltage and force in a circuit. And there are different types of sensors, such as strain gauge and piezoelectric sensor, etc. There are two important response properties in force transducers. First one is linearity. Linearity determines the quality of a force transducer. And then linearity is determined from the correlation coefficient. As you can see here, so force and volt here, so linearity here. If the relationship between force and volt is linear, and the slope is sensitivity, which can be used to convert from the measured voltage into force in Newton. And there are also two important considerations. The first one is range of forces. This range of forces should not be too small. Otherwise, as you can see here, a high value of force cannot be measured. And crosstalk as well. And this one needs to be managed using calibration, the metrics provided by the manufacturer company. Among the various force transducers, let's talk primarily about Forceplate, because this Forceplate is the most commonly used force transducers in the field of biomechanics. There are a total of 10 elements in force plate. Okay, Fx, Fy, Fg, three components from ground reaction force. So Fx, Fy, Fg, and then moment component, Mx, Mi, Mg. Here Mx, My, Mg, and this is a moment caused by ground reaction force about the true origin. So we'll talk more about this one soon. Tg is a free or twisting moment about the vertical axis at center of pressure, right here. And then Cp, center of pressure, x, y, z. And z is typically 0. So among 10 elements, we are interested in only 6 elements, highlighted in red here, Fx, Fy, Fg, and Tz, and then x, y of center of pressure. And let's take a look at how the 6 components of interest can be obtained. First of all, you can see foot-ground reaction. This is force plate here, and then foot here. You can see these arrows here. These are all the foot-ground reaction according to Newton's third law of motion. If a force has a contact with the ground, the foot is supposed to receive reaction from the ground. That's why you can see this foot-ground reaction. And there are 4 sensors in the force plate, each one at each corner, okay, right here. And then the foot-ground reaction can be quantified by these 4 sensors. So these distributed forces throughout this foot obtained from the foot-ground reaction is equal to the sum of all forces coming from these 4 sensors. Then the sum of the forces from the 4 sensors generate a single ground reaction force and free torque about the vertical axis, and center of pressure can also be measured. This slide shows how to calculate a twisting moment. Since Tg, this is a moment, we need to use the moment produced by the ground reaction force. Here M means the total moment caused by the forces coming from the 4 sensors. It is broken down into 3 components, such as Mx, My, Mg. Then these are directly provided by the force plate. And then we have to add all the moments produced by the 4 sensors. That's why we have to use a sigma here. So I is equal to 1 to 4. So as you learned, so in order to calculate moment, we need to have a position vector and force vector. So R cross F. So this part is the moment caused by the first sensor, and this is a moment caused by the second sensor, and moment caused by the third sensor, and then the moment caused by the fourth sensor. And sum of all these moments is equal to the moment caused by the ground reaction force above the true origin plus a twist moment. And then this equation can be solved for Tz to calculate Tz value here. Strain gauge type force plate manufacturers provide a unique calibration matrix for each force plate. And then this matrix is for managing crosstalk. And then this matrix is a result of a series of computerized calibrations performed at the factory. This is the calibration matrix, and then the diagonal terms are the actual calibration coefficient, and off diagonal terms are the crosstalk terms. And then we got this value obtained from 6 channels of the force plate. And then once we get this, by multiplying this value by this calibration matrix, we will be able to manage the crosstalk. This is the final value. In general, the true origin of the strain gauge force plate is not the geometric center of the force plate due to problems in the manufacturing process. That's why the manufacturers usually go through a series of calibrations and estimate the position of the true origin. So we need to define the center of pressure not relative to the geometric center of the force plate, but relative to the true origin. Here RCP means the position vector of the center of pressure relative to the geometric center of force plate, And the R0 means the position vector of true origin relative to geometric center of the force plate. And then this true origin is provided by the manufacturer. And here RCP minus R0, this one will give us the position vector of center pressure relative to the true origin. Here we got XY0. This is the center pressure component here. Again, ABC, this is provided by the manufacturer. And then we got ABC. If then RCP minus R1 will be X minus A, Y minus B, and minus C. This slide shows how to calculate the center of pressure and TG, which is the twisting moment, based on the location of the true origin. And as you learned in the previous slide, so moment is equal to R cross F plus twisting moment. Here R is the position vector. And since we already defined the true origin, this R must be RCP minus R0, which is the position vector of center pressure relative to the true origin. And then we got this component here, X minus A, then Y minus B, and then minus C. And this one is the position vector of center pressure relative to the true origin. And then this vector form can be expressed in this matrix form. So that M has 3 components, and then F also has 3 components. And then this is again column matrix for this TG vector here. And then this position vector of center pressure relative to the true origin can be expressed as here using skew symmetric form of this position vector. And then you can do some matrix multiplication. Then you can get this value. This is nothing more than a simple just matrix multiplication. Here, this mx, mi, mz, and the fx, fi, fz, these are directly obtained from the force plate. And then the second row can be solved for x, because x is x component of center pressure. And then this first row can be solved for y, because this is y component of center pressure. And the third row can be solved for Tg. This is our one of the value of interest, the twisting moment. And as I mentioned earlier, all My and then Fx, Fg, and Ac as well. This is again true origin component. And then these are all known value. This is unknown. So we'll be able to calculate x. And then this one result, y is unknown value. Again, the y component of center pressure. And these are all known value. So we will be able to calculate this value. And this one as well. So once we get the x and y from this calculation, this part will be unknown value. Then we'll be able to calculate Tg twisting moment. There's an issue in ground reaction force. The center pressure can be very sensitive to errors in the moment and force component for small fg value. This is why we can get the erroneous center pressure coordinate at the beginning and end of contact phase, where fg is fairly small. For this reason, so we need to set the threshold for fg. Typically, we set the thresholds as 10 newtons. So if fg is smaller than the threshold, the program does not generate the center pressure coordinate. Okay, this is the end of the overview of ground reaction force. Then we will take a look at some research studies performed using ground reaction force.